morning. Welcome to lecture 30. Today's lecture is about computer simulation of fading channels. So if you look at the material that we have covered so far, our goal has been to understand the nature of the wireless channel. We have understood that there is the phenomenon of multipath. Then we also understand that because of the phenomenon of multipath, you have the resultant signal fluctuations, which we refer to as fading. So in real life, you will encounter channels that are wireless channels, which are channels which have fading and which will have time dispersion. Now, we have been able to characterize them through the Whiteson stationary uncorrelated scattering model. We have the coherence time, coherence bandwidth. We've got the entire panorama of understanding the wireless channel. The goal of this, of the end of last lecture and today's lecture, is to show how do we mimic these channels on a computer so that we can then assess the performance of the different systems. So in this context, if you remember, we said that there are some practical channel models that are COST 207, the ITU-R. These are all models that are used in the industry in standards to mimic these wireless channels. Now, yes, we understand what the COST model is. How do I actually implement it on a computer? So it says that there are many taps. Now these taps have to be generated using a fading process, multiple number of taps, each of them with different power levels, different delays, which I have to generate. Now the block that we finally have to worry about is how do I actually generate a Rayleigh fading in a computer? Because it's a random process. How do I, the only things that I can do on a computer are, are limited in terms of, so how do I manipulate the tools that I have on a computer to achieve the goals that I have, to make a fading waveform that looks very similar to what you would see in a fading channel. So that's the goal of today's lecture. As we saw in the last lecture, there are two methods that, in fact, I would say it's more like one method, the filtering method. So if you could combine these two, I would say that these two are based on the implementation of a filtering approach. You take white noise, you pass it through a filter which has got a certain spectral shape. The spectral shape will give a coloration to the noise, and coloration is the same as correlation in the time domain, and the correlation is the Bessel function that we are interested in. So basically the filtering approaches are the Clark and Gans method, and the Smith method is an efficient implementation of a Clark and Gans. So to just summarize the Clark and Gans method, we are generating white noise, two independent white noise sources, uncorrelated white noise, basically the successive samples are uncorrelated. We will pass them through a filter which will introduce for us the appropriate coloration of the noise. Coloration in the spectral domain is the same as correlation in the time domain, so therefore the output of these two sequences have got the Bessel correlation. Okay. But again, the Bessel correlation is not what you actually need it for the complex channel. So basically we need to worry about how to establish it for the complex channel. But what we have is the upper branch I treat it as ZR, the lower branch I treat it as ZI, multiplied by J, add them together, that gives me a complex channel gain. Now these have been appropriately correlated in their the real part with itself, imaginary part with itself. Now we need to confirm that the overall correlation is obtained as expected, and it's not surprising that because they are independent, what you'll be left with when you compute the correlation will be the correlation of the real part and the correlation of the imaginary part, and therefore things will work out. But we have to verify that. Today's lecture has got a lot to do with the verification aspects. Okay. So the Clark and Gans method basically has two sources, each of them appropriately filtered, multiplied by J. Now some of the challenges that we observed with the Clark and Gans method, and in general the filtering approaches, is that this is a sharp filter. A sharp filter will give you a long impulse response, which means that you will have to do a lot of computation to compute a small segment of data. You have to do a lot of computation. The other challenge is that Doppler may not be known ahead of time, so you cannot pre-compute these filters. You may have to compute them in real time. So basically different filters will be needed. And of course, we also saw that once you have these long filters, you don't have too much flexibility in terms of the length of the fading waveform that you are generating. You will be constrained to generate a minimum set. So that is Clark and Gans. Clark and Gans basically does a time domain convolution. The Smith method is the same approach but implemented in the FFT domain. You take the Fourier transform of a block of data, xr of n, take the filter, take its FFT, multiply the two and get the inverse. But we also made the observation that I don't have to take the FFT of the Gaussian samples. I can generate them directly in the Gaussian domain, provided I retain the symmetry so that I get the appropriate real values in the time domain. So basically I directly generate xr of k. Hd of k, I have generated the samples of that. So I don't generate an impulse response. I just sample the spectra, the power spectral density. So this is what gives me Hd of k. So it's a very simple process. I generate n Gaussian random variables. I have sampled the spectrum of the power spectral density, and then I multiply, take the inverse FFT. That gives me a sequence of length. Now one of the constraints that we ran into was the size of the FFT. The size of the FFT depends on what is the spacing that you want within the window of interest, basically from minus FD to FD. And the other one that is constraining you is f sample, is the sampling frequency divided by 2, that corresponds to pi. So basically the size of the FFT is f sampling divided by delta f, and that is going to determine the size of FFT. That's also going to decide the length of the waveform that you will generate through this process. So we made the observation that very often in simulation we are not interested in very long fading sequences. We are looking at independent sequences of fading waveforms of shorter duration. So the question is there a better method? And the answer turns out to be yes, and that's based on the Jakes model, and that's what we will focus on today. So is the context clear? We are trying to implement fading in a computer. We basically have only a limited set of tools that we can use on the computer, but we want to be able to generate the time domain sequence with the appropriate time domain correlation, with the appropriate spectral shape, with the flexibility of generating any Doppler, any length of sequence. That is the goal that we want to do today. Okay, so the task before us is to look at the Jakes model. As I mentioned to you, William Jakes was one of the pioneers in terms of the wireless communication. His book on microwave microwave communications is considered one of the best references for the early work that is done in this field. So let me capture for you the essence of Jakes model. It consists of a number of oscillators. Oscillators are deterministic. Once you set the frequency, the oscillators are a very predictable waveform. But what makes it somewhat random is, notice that there are some phase terms. Each of these oscillators has got a phase term except one of them, and these phases will be chosen in an appropriate manner to ensure a randomness. And there are some gain terms which are applied to the oscillators, and one set of gain terms are added to get the imaginary part, another set of gain terms are added to get the real part. So basically the goal is to see whether this structure achieves the goal for us, and it turns out it achieves it in a very nice manner, but today's lecture is that. So what are those oscillators? So basically Jakes method, let me just start by writing the following. Jakes method consists of a number of oscillators. So we first specify a number of oscillators. So there are a total of n0 plus 1 oscillators. Now n0 has got a specific property, n is equal to 4 n0 plus 2, where that basically means that n is a multiple of 4. It is even but not multiple of 4. So this is an even number but not a multiple of 4. That's what this means. Now there is a very specific reason why it is chosen that way. So n naught happens to be a number, and for any integer number would satisfy this relationship. N naught greater than or equal to 15 turns out to be the thumb rule for good modeling of the fading channels. Okay, but again, the interesting part is how the entire framework is derived. So now these oscillators, there are n naught plus 1 of them. The different oscillators are given in are defined in the following fashion. The maximum Doppler times cosine 2 pi by n into n is equal to 1 through n naught, and then there is a final oscillator which is at the Doppler frequency. There are n naught of these, and then the final one has got it's basically at f Doppler, maximum Doppler. Okay, so that is what is represented for us. The amplitudes of those oscillators are what is given. Again, an interesting observation. This corresponds to the maximum Doppler. All of them, that one has got a slightly lower amplitude than the others, and interesting for us to visualize how that will play a part in the overall picture. But a more intuitive way to understand the oscillator frequencies can be seen in the following form. But first, let's interpret what are these different oscillators. So basically, you will have fd cosine 2 pi over n, that will be equal to f1. fd cosine 2 pi over n into 2 will be f2 dot dot dot. I want to know what is the last oscillator, f of n naught. That will be fd cosine 2 pi over n times n naught. I would like to rewrite or simplify this in a little bit better manner. So you can rewrite this as n naught can be written as 1 by 4 into n minus 2. Am I right? Or it can be written as n by 4 minus 1 half. So basically, if I can write it in this form, I can show that this last oscillator is actually equal to fd cosine pi by 2 minus pi over n. Pi by 2 minus pi over n. That's the, okay. So this the mathematical expressions can be nicely understood if you were to visualize it as one quadrant of a circle. This corresponds to Doppler fd, the full length, the radius of the, and then you are going to take at different angles. So the angles are at 2 pi over n, 4 pi over n, that's your second one, and then the final one happens to be at pi by 2 minus pi over n, almost at pi by 2. Pi by 2 minus pi over n. Basically, you take their projections, that will be the oscillator frequency. So the highest frequency is fd, then you have this is f1, then the last one is f of n naught, right, in our notation. So the one with the smallest frequency will be f of n naught. So basically, Jake's method requires us to use a set of oscillators. The frequencies have been understood. There is an oscillator at fd, and then there are several which correspond to uniformly spaced in the angular domain. Okay, and then their projections onto the real axis, that length gives you the actual frequency of the oscillator. Okay, is that clear? That's basically what the oscillator frequencies are. So now let's go back and plug in to the system the oscillators. So basically it's cosine 2 pi f1 t times phi 1, and similarly all the n naught oscillators, and then the last one consists of a oscillator at the Doppler frequency. So what I would like you to write down are, if you call this as let's call this as ZR of t, this as ZI of t, and so therefore what I would like you to write down is an expression for ZR of t. ZR of t, each of these multipliers has got a scale factor of 2. So 2 I take out as a common term, summation n is equal to 1 through n naught, representing the n naught oscillators. It is cosine beta n cosine 2 pi f n times t plus phi n. Okay, that captures the n naught oscillators, plus the last term has got square root of 2 cosine alpha cosine 2 pi f dt. In the figure I have used fn. Fn is the same as fd, the notation that we are using. Okay, so this is the expression for ZR of t. Of course, there is a scale. There's a scale factor. We will maybe you should write that down. 1 over scale 2 times this one. We will not worry about the scale factor at the very end. So write down the expression for Zi of t. It is 1 over scale 1. Expression very similar, 2 times summation n is equal to 1 to n naught. Now it is sine beta n. Oscillators are the same, cosine 2 pi f n t plus phi n plus root 2 sine alpha cosine 2 pi f d t. Okay. So now the setup is more or less complete. The claim is that if you combine ZR of t plus j times Zi of t, you will get the properties that that we are interested in. What are the properties that we are interested in? Expected value of ZR squared of t is equal to expected value of Zi squared of t must be equal to 1/2. Expected value of Z of t, Z star of t plus delta t. This is equal to some constant times j naught 2 pi f d times delta t. It's a Weizmann stationary process. Okay, that this will be satisfied, and probably not clear at all why this should satisfy, why this should even look like a random process, and the whole thing hang together. So to summarize what we have said so far, there are a set of oscillators whose frequencies have been very carefully chosen as uniformly spaced samples along the first quadrant of the circle. They are integrated into a structure where phase terms have been added, and then multipliers have been added, and then you are adding them together to get the waveforms that are of interest. Okay. So let's quickly verify some of the parameters of interest and build from there on. So the first task that we have is to answer this question: is it zero mean? So expected value of ZR of t, and as in many of the stochastic systems, we will replace the expected value with a time average. So if you can show that the time average is satisfies the property, then the process that you are working with satisfies the property. So basically, I will use this as this is denote time average. So the first task for us is to look at the time average. So time average of ZR of t, does that go to 0? So basically, if you were to look at the time averages, you will find that it is a sum of sinusoids, right. If you have a sum of sinusoids and you take its time average, it will go to 0, guaranteed, right. So it does not matter, the random phases really do not matter, the scale factors really do not matter if you have a sum of sinusoid. So basically ZR of t is equal to sum of sinusoids. So one part of the property sort of is very obvious for us to verify. Similarly, Zi of t, you can by the same argument both of these will be 0. So therefore, the processes that we are working with are 0 mean. Zr of t and Zi of t are 0 mean. Okay. The second property that we need to verify is that they have variance equal to 1/2. So now this is a non-trivial verification that we need to do. So and this is where you can see Jakes gave himself several degrees of freedom to satisfy this property, because it is non-trivial for us to satisfy. So if you were to go back and look at the model, where are the degrees of freedom? The degrees of freedom, since your frequencies are fixed, the degrees of freedom are in the phases that you have and the scale factors that you have. Those are the degrees of freedom, and of course the scale factors, but by and large the property hinges on the so let's verify the and again it's a very instructive exercise. I will skip some steps, but I would request you to definitely validate that. So I want to now look at the time average of Zr squared of t. Okay. We need to have the expressions for Zr of t and Zi of t readily available. So let me just write down Zr of t once more. This is 2 times summation n equal to 1 through n naught cosine beta n cosine 2 pi Fn t plus phi n plus root 2 cosine alpha cosine 2 pi Fd t. Correct? Okay, that is the expression. Again, you can write down for Zi. All the explanations I will do using Zr as my reference. Now comes the sort of the careful task of squaring Zr squared, squaring Zr. So which means that there is a summation term which you will have to square, so you will get lots of cross terms, and then there is one extra term which will multiply with all the terms in the summation, and then it will get squared itself. So basically you will get a large number of terms, some of them are square terms, some of them are cross products. Okay. First observation, all those terms which have got a multiplication of 2 cosine terms of different frequencies. Product of 2 cosines will give you sum of 2 cosines, which means when I do time average, those will go. So what I am left with is only those terms which are products of self terms, basically square terms. So what we have is I would now have to take the time average, square of each of the terms in the first part will be 4 times summation n equal to 1 through n naught cosine squared beta n cosine squared 2 pi Fn t plus phi n plus 2 times cosine squared alpha cosine squared 2 pi Fd times t. I have to take the time average of that. Okay. Again, just make sure that you are comfortable with the terms that are being written down. So cosine squared 2 pi Fn t plus phi n. I am going to simplify this term in the following manner. I am going to write it as 1 plus cos 2 theta by 2. So this term can be written as 1/2 of cosine squared beta n. Keep that, I am not touching that. The other one becomes 1 plus cosine 4 pi Fn t plus 2 phi n. correct? Notice that this is also a cosine term. When I take the time average, that is going to vanish. So this entire term becomes a time average of 2 summation times summation of n equal to 1 to n naught cosine squared beta n, that's basically the first term that is coming out, plus cosine squared alpha. Wait, I think I've made some mistake. Oh, no, it's correct. 2 times cosine squared beta n plus cosine squared alpha. Okay. So this can, I need to take the time average, but basically there is no time dependence on this. This is the expression that we have as the time average of ZR squared of t. That is equal to summation n is equal to 1 through n naught. 2 cosine squared beta n, I am going to write it as 1 plus cosine 2 beta n plus cosine squared alpha. Okay. So this is the expression that we have for ZR squared. Okay. Please verify corresponding result. Please verify this first. Also verify the following: Zi squared of t, time average. You get something very similar. Summation n is equal to 1 through n naught. The corresponding expression, I will write it for you in a minute. Please derive the result for expected the time average of Zi squared plus n naught. Okay. Now let me quickly do the next step of, or maybe we can write it down here, n naught minus summation n is equal to 1 through n naught cosine 2 beta, basically it will be 1 minus cosine 2 beta n, cosine 2 beta n, and then the outside term is sine squared alpha. Okay. So basically the difference, this is equal to n naught plus summation n is equal to 1 through n naught cosine 2 beta n plus cos squared alpha. Okay, that's the first term. Please verify that you get these two terms. Okay. Now for the, I hope you've been able to get up to this point. Next is a very crucial step. This is where the beauty of the entire model lies, the choice of the degrees of freedom. Choice. Alpha is chosen to be equal to 0. Beta n is chosen to be pi divided by n naught plus 1 times n, where n is equal to 1 through n naught. Okay. So basically I would now show a result which will be very helpful for us to simplify the earlier expression. The result is, if I do summation n equal to 1 through n naught e power j 2 beta n, notice it is in the form of a geometric series. Okay, so the summation is quite easy, except that the starting term is not 1. So to compensate for that, I am going to say n equal to 0 through n naught e power j 2 beta n. I introduced n equal to 0, which means that I have to subtract the first term, minus 1. So basically these two are equivalent. Okay. Write down the result of the geometric series. There are n naught plus 1 terms. This comes out to be 1 minus e power j 2 times pi over n naught plus 1 into n naught plus 1. Okay. Denominator 1 minus e power j 2 beta n. The important thing to remember is that this numerator term is, this is equal to 0. There's a minus 1 sitting there on the right side. The reason for this is, what is this one? This is cosine 2 beta n summation n equal to 1 through n naught plus j times sine 2 beta n. This is equal to minus 1. So, which means that the expressions that we have, summation n is equal to 1 to n naught sine 2 beta n is equal to 0, summation n is equal to 1 through n naught cosine 2 beta n is equal to minus 1. Okay? But this is the result that we are interested in, because this shows up in our expressions that we have derived earlier. So, this cosine 2 beta n is present in those two terms. So, basically what this says is that mod ZR squared of t, if I choose my alpha and betas in the following fashion, can be shown to be n naught minus 1 plus 1, that basically will be equal to n naught, mod Zi squared of t will be equal to n naught plus 1. Okay? So, if I choose scale 2 to be equal to 1 over root n naught and scale 1 to be equal to 1 over root of n naught plus 1, go back to the Jake's model. Scale 1 and scale 2 have been appropriately chosen, then we can put a tick mark that you will satisfy, because the time averages satisfy the value equal to 1/2. Okay, I made a small mistake, you should make it 1/2. Okay. So, normally the variance would have come out to be n naught. If I do a scale factor of 1 by root n naught, that will make it unit variance, but I want variance of 1 by root 2. 1 by 2 n naught square root, okay, and this also will be square root. Okay, so that will give me the appropriate variance that I need, and will satisfy the second property. Okay. Now, the most crucial in our entire discussion is going to come in terms of our verification of the third property, which is probably the most non-trivial of that. So, if I take the autocorrelation of Z with itself at t and t plus delta t, okay, the reason I am writing this is I do not have a guarantee that the waveform that I have generated is Whiteson stationary. I cannot straight away write it as delta t. So, I am going to measure the correlation between at time t and t plus delta t. This is going to be expected value of z of t, z star of t plus delta t. I am going to approximate this with the time average of ZR of t plus j times Zi of t, that is the first term. Second term, ZR of t plus delta t, because of the conjugate sign it becomes minus j Zi of t plus delta t, time average of that. Okay. Now, you have the expression for ZR, you have the expression for Zi. Please plug in the terms and use the same property that we have used before. Basically, if you get a cosine of two different frequencies, it will become sum of two. It will become a sum of two cosines with the sum and difference frequency. Time averages will send them to 0. What will be left are those terms which are the same frequency present. Okay, we need to simplify those and then come up to the final verification to see whether this gives us some constant times j0 2 pi fd times delta t. Okay. It is an absolutely brilliant model. As you derive it, you will start to see, you said, my goodness, this guy must have been a genius to figure this out. Okay. But it's one of those things where only if you go through that, that's why I felt it was important that we should take the time to derive it. So, I will leave it at this point, request you to please try out and will give you sufficient hints. I will assume that you have been able to get the expression for RZZ. The final step of showing that it is equal to the Bessel function will be our first task for tomorrow. Okay, so please do make an attempt to get an expression for this, and at least once you have come up to that point, we can then we can show that it is very easy. It is easy for us to develop it into the final step. So just so that you can verify, RZZ of t, t comma t plus delta t will come out to be the following expression: 4 times summation n is equal to 1 through n naught cosine 2 pi fn delta t plus 2 times cosine 2 pi fd times delta t. Okay, it's actually a very compact expression. It is very close to you start to see the relationship to the Bessel function, but the actual proof of showing that this is an approximation to the Bessel function will be our last step. But please do show that RZZ of t actually is obtained. If in case you are having some difficulty, no problem, I'll give you a few hints at the start of tomorrow's lecture and then go on to the final discussion. I'll have to end the lecture today. I'll pick it up from here in tomorrow's class. Thank you.